Hello, welcome back to the class of control or linear system. In the last class I teased you at the end with the idea of stability, and stability is the topic of this class. So you might already have an idea of what stability is. Stability is a very important concept in the context of dynamical system and linear systems. But you might have already discovered it in mechanics or other disciplines related to the concept of an equilibrium. So stability is the property of an equilibrium. You remember what an equilibrium is. You have a dynamical system with some input and some outputs. The notion of equilibrium is to have a solution of the system for a specific input which does not change with time. So basically where all the time derivatives are zero, so which in mechanics correspond to a system that does not move at all. So let's look at these three pictures over here, which represent three possible cases of equilibrium, which correspond in general to the three possibilities, three characteristics of stability of first an equilibrium, and then later on we'll see also a system. So imagine this red ball is sitting on top of a table with weird shapes. You have three possibilities. The first one over here is called a stable equilibrium. How do we judge the stability of an equilibrium? Basically the trick is to perturb the equilibrium a little bit. So in this case, to push the ball a little bit. So in this case the ball will just move back to the equilibrium position, and this is called a stable equilibrium. If you do it here instead, the ball will just fall down and go very far from the equilibrium, and this is called an unstable equilibrium. The third case is something in between. If you kick a little bit this ball, it will go a little bit off. It will not go back to the equilibrium, but it will also not go indefinitely far away. So this is what is usually called a critically stable equilibrium. For linear systems, we also talk of stability of the system itself, not only of its equilibrium. Why we do this? It's a bit of a sloppy definition, but it's due to the fact that linear systems, unlike nonlinear system or unlike any generic mechanical system, linear systems have all the equilibrium which are the same. So if a linear system has stable equilibrium, then all the other possible equilibria of the system will also be stable. So in this case it makes sense to speak of the stability property as a property of the system and not of the specific equilibrium itself. That's why we talk of stability of linear system. Remember, this does not make any sense when speaking of nonlinear system in general, where instead you have to look at each specific equilibrium point. For linear systems, the notion of equilibrium, which we refer to and which is probably the most useful at this stage, is a slightly different notion of stability with respect to the one that is probably conveyed by this picture over here. It is a notion of stability based on input-output properties. That's actually what we did so far. We defined systems, linear system, as input-output machine, let's say, something that gets in an input and gives an output, so it makes a lot of sense to define stability with respect to the signals. And so the typical stability notion which we look into is the so-called bounded input, bounded output, or BIBO stability, which means that if you have a signal going in as input which is bounded, okay, it never goes outside the certain plus and minus tunnel, okay, it never goes beyond or below some max and min value, then the output will also feature the same property. So if a system satisfies for all bounded input the fact that all outputs are also bounded, then it is called BIBO stable, otherwise it is not. So how to assess whether a system is BIBO stable? Well, you can do simulation. You could put all the signals inside, all the possible signals inside the system and look at the outputs, but you will need to do an infinite number of tests, so this is not a practical criteria. We look for practical criteria, and the first one is the criterion of the impulse response. Basically, this criterion says that a system is BIBO stable, a linear system is BIBO stable if and only if the impulse response is goes to 0 for t going to infinity. So you remember that the impulse response of a given system for example, in terms of transfer function, is basically the inverse Laplace transform of the transfer function. So if you have a system described by a transfer function h, basically the inverse Laplace transform h of t is the impulse response. Well, if the limit of the impulse response for t going to infinity is 0, then this system is Beebo stable, otherwise it is not. This criterion is nice. Would require you to compute the impulse response of the system, which actually is not really necessary, and then you can derive a second criterion which is slightly simpler to use based on the same idea, which is basically the second stability criterion based on the poles of the transfer function. So the proof is very simple, the idea is very simple. The impulse response basically depends on the poles of the transfer function. So you remember the inverse Laplace transform of h of s is the impulse response. So if you have a transfer function over here, like this, general transfer function with the numerator and the denominator, you want to compute the inverse Laplace transform of this, which is the impulse response. Why we want to do this? Because we want to compute the limit. We want to see how it goes for t going to infinity. So what we should do, we should just basically decompose this term as the sum of elementary terms. And basically, if you do this, you have to basically decompose the denominator in terms of factors, and then you will see the poles appearing, the alpha, and the multiplicity of each pole also appearing over here. And then if you continue, you just look at your table of inverse Laplace transform, then you will see that each elementary term making up this decomposition would basically have basically yield in terms of inverse Laplace transform terms like this with an exponential with argument the pole times t times some polynomial terms which go up to the multiplicity of the pole minus 1 and some constants. Now the constants are not so important because we are just looking at the trend, whether these terms go to infinity or not. So what is interesting maybe is to develop this exponential, which is in general a complex exponential because we have alpha which could be complex. So basically this term is equivalent to this. There is a sinusoidal part depending on the imaginary part of alpha, which is not so important for us, but what is more important is there is a genuine exponential term depending on the real part of alpha. Now this thing h of t made up of the sum of these terms goes to 0 if and only if all of these terms goes to 0, and this happens if and only if all the alpha I have a negative real part, because we need to have this exponential going to 0, and this happens if this is negative for t going to infinity. So basically this is the reason for the second criterion. The second criterion, what does it tell you? Well, you can read it here. A linear system of transfer function h of s is bounded input, bounded output stable if and only if all of its poles have strictly negative real part. So basically if you have a transfer function, you just look at the denominator, you compute the poles of the denominator. What are the poles? Remember the values of s which make d equal to 0, and if all of these has strictly negative real part, notice strictly, then the system is Beebo stable. If you happen to have just one pole which is not strictly negative, either positive or 0, then the system is not Beebo stable, which is equivalent to saying that the limit for the impulse response does not go to 0. Now you might have different cases according to what this limit does, if it does not go to 0. So let's look at this table, and please pay attention to what I'm trying to explain here, because these definitions sometimes are key to understand what we want to say. So if what happens if the system is not Beebo stable? Okay, so if the poles of the transfer function are all strictly negative, then the system is Beebo stable. What if it's not the case? Okay, it is not unstable all the times. Okay, so let's just remember this. unstable is not the contrary of BIBO stable. If a system is not BIBO stable, you might have different outcomes, and this is the list of the possible outcomes. So if you have one pole, at least one pole, which is strictly positive real part, the system is unstable, which means that the impulse response will go to infinity exponentially. Now, if this real pole, if this pole, which happens to have a positive real part, is a complex conjugate pole, as you might see here, you have a real part strictly positive and also an imaginary part which is non-zero, then the system will go to infinity, the impulse response will go to infinity with an oscillating behavior, with an oscillating response, which is also meaning that the system is unstable. If you happen to have a pole which is exactly zero, or a couple of complex conjugate poles which are also featuring a zero real part, all with multiplicity equal to 1, all with multiplicity equal to 1, I'm stressing this one, and all the other poles have strictly negative real part, then this system is critically stable, which means that the system impulse response will not go to 0, so the system is not BIBO stable, but it will not go to infinity either. That's why we call it critically stable, which is not BIBO stable. It can also be called marginally stable or marginally unstable. You kind of see anything in the literature, but it is important to understand that it is not BIBO stable. Okay, we will see this in example later. And then if you have poles with real part equal to 0 with multiplicity higher than 1, so for example a double pole in 0, then the system is really unstable, is going with impulse response going to infinity. It goes to infinity though with a polynomial response, not with the exponential response, for what it matters. So let's see some examples. Now you understood the criterion. The criterion is how do we check whether a function is stable, BIBO stable or not? Well, we look at the poles, we look at the real part of the poles. All the poles have negative real part, fine, we are BIBO stable. Otherwise not. Not means that you can be critically stable. If you have poles with real part equal to 0 but multiplicity up to 1, or genuinely unstable system if you have at least multiplicity 2 for a real part equal to 0, or at least one real part which is positive. This speech is just what was appearing in the last slide. So I challenge you now, have a look at these functions over here and take the time to answer my question for each one of them. Are they stable, BIBO stable or not? And if not, what kind of stability property do they have? And also try to figure out what could be their impulse response. This graph over here basically shows you where the poles should be located in order to have stability. Basically should have a negative real part in this green area. So I'll give you the time to try it yourself, to answer all of them. So please feel free to stop the video now and try and answer, and the solution is coming up just afterwards. Solution in 3, 2, 1, let's go. So let's look at the first one. Well, first one, which are the poles? Well, the values of S making the denominator 0 are obviously -1 and -2, real and negative, so BIBO stable, and the impulse response is something that goes to 0. No problem, very easy. Let's go to the next now. In 3, 2, 1. Next one, well, this one, I don't know what it does, but I can see very clearly that here we have a positive pole, because we have 1. So we have an impulse response that goes to infinity exponentially. Actually, I can find out what this one does, but I want to stress that for being unstable, you just need one pole with a strictly positive real part. So I don't need to bother to look into this other part over here. Let's move to the next in 3, 2, 1. So this one, well, you can compute very easily the solution of the denominator. It is a pure imaginary solution. So pure imaginary solution means 0, but 0 real part, but with multiplicity 1, because you have a couple of complex conjugate poles. It's basically square root of 3 times g plus or minus. So this means that the system is not bivostable. We are in the case of critically stable with an impulsive response, like this. This is the impulse response. Never goes to 0, but never goes up either. Now let's move to the last one in 3, 2, 1. So this last one is a bit more complicated. Let's have a look of the denominator. This one, the pole is -2, no problem. This one also, you can compute it, and it corresponds to two complex conjugate poles with negative real part, so also no problem. Actually, the trick to get rid easily of degree 2 terms is to look at the sign of the coefficient. If all the coefficients have the same sign, then it means that the poles have negative real part. If all the 3 coefficients appear, okay, with the same sign, none of them is 0. Huh? So if you have this one positive, this one positive, one positive, no problem, this thing will be stable. What we are left with? We are left with a pole in 0 with multiplicity 2, which is the case, what we said, of not bivostable system, and due to the multiplicity equal to 2, we have an unstable system. So the response diverges polynomially, we said. In fact, it diverges, as you can see, with a linear curve. Okay, so now let's move to another criterion, which is the most difficult criterion to know, and I also would say it is the last resort criterion, and it is taught in this class only for historical reasons, we would say, because what is the purpose of this criterion, which is called the Routh-Horowitz criterion? Well, let's look at the example over here. In all of these examples, even if the denominator is of high degree, like here is 2, not so bad, but here is 3, here is how much? 5. In all of these cases, it has been very easy to find out which were the poles, because the denominators were already factorized. You can read the factors directly and compute directly the solution. But if you have a denominator which is just written out with the coefficient, like something times 2s power 5 plus something s to the power 3, etc., well, it's not easy to compute the poles just by looking at the denominator if it is not factorized. So that's why it can be useful to have some practical criteria, some kind of recipe that can allow you to understand whether a denominator features stable or unstable pole, let's say like this, feature a stability or not, even without computing the poles by any method you have. That's why I say this is a bit of a legacy kind of teaching, because nowadays you can just take MATLAB and ask MATLAB to compute you the poles of a transfer function, and it will give you the solution. So this Routh-Horowitz criterion, of course, has been invented when there was no availability of computers like this, and that's why it was very useful. But nowadays the importance of this criterion is a bit, let's say, less relevant, although there could be still some interest in using it for computing let's say the solution, the stability properties of a system in a general case, when instead of having just number coefficients you have like a parametric coefficient. We will see an example later on. Anyway, what is it about? So to make a long story short, you can use this Routh-Horowitz to determine whether a polynomial is a polynomial, so the denominator of a transfer function corresponds to a stable transfer function or not, just with a simple algebraic recipe. and basically the recipe consists in compiling a table. So I stressed again, this is nice to know, it is useful for some cases, but it is really the last resort of the criteria if the other criteria which we have just seen before, and maybe the other criteria which we'll see later on, do not work, because it is kind of takes some time to do, as you will see. So the root-Hurwitz criterion requires compiling a table, basically. So how do we do this table? So the table depends only on the denominator, okay? Because as we see, the stability of the transfer function of a system depends only on the denominator, so you can just forget the numerator and just look at the denominator. So the idea is that you take the highest value, the highest order or degree of S, and start writing a table with S to the power n over here, then S to the power n minus 1, and you go down until you reach S to the power 0. And then here what you write the coefficients of the polynomial of the denominator, taken one yes and one no. So you start an, then an minus 2, an minus 4, and in the second row you start with the second one, an minus 1, an minus 3, etc., etc. Then you continue creating these lines until S to the power 0, as I said, by using this procedure here from the previous two lines. So basically you can see this term over here, it's a bit complicated, the expression, but you can take the time to read it and digest later on. But basically you have to do this one times this minus this one times this, divide by this one. For this one it is this one, sorry, this one times this one minus this one times this one, divide again by this one, etc., etc., until you fill all the line. And then you continue for the following line, just use the same pattern, apply to the previous two lines. So when you finish the table, basically you end up with a table like this, filled with number, and the criterion says that the linear system is Bibot stable if and only if this root-Hurwitz table has all the elements in the first row of the same sign, okay, all positive, all negative, okay, and that's it, basically. That's it. The number of sign change is equal to the number of positive real part roots, but that's not so important. We are just happy to know that the system is not Bibot stable. And there are also some very special cases which we will see later on, but let's see first an example of how this works. Or actually you can try and do it yourself if you wish, if you're really up to the challenge. So I provide you this transfer function, and then we'll see the root-Hurwitz table of this one. I'll let you try it yourself, so please stop the video if you wish to try it, and the solution will be shown in 3, 2, 1. Okay, so how we do it? Well, we said we start writing down S to the power 4, S to the power 3, etc., etc., S to the power 0, then coefficient 1, 1, 1, and then 1, 1 for second row. So first row 1, 3, 1, second row 1, 1, and then we start with the third row by using that rule you've seen before. So the rule is for this term 1 times 3 minus 1 times 1 divide by 1, 2. For this one over here, 1 times 1 minus 1 times 0 divide by 1, 1. Here what we get, 1 times 0 minus 1 times 0, so 0. Okay, so now we move on. Next row, this term over here, it is given by 2 times 1 minus 1 times 1 divide by 2, which basically gives 0.5. And this one will yield 0 because it is 2 times 0 minus 1 times 0, 0, etc. Then last term we get 0.5 times 1 minus 0 divided by 0.5, which gives us 1, and we are finished with this one. So all the terms are basically positive, so the system is Bibot stable. That's it. There are two special cases now which we have to consider, and I want to go through them a little bit briefly. Basically, the most common special case is if at a certain point you happen to have a row with a 0, starting with a 0, before the end of the table, before you reach s to the power 0. So basically then what you do, you replace the 0 with a letter, an epsilon, and then you continue with this letter, and at the end you will compute the sign of the row just by taking the limit for epsilon going to 0 on the positive side, let's say. And if all the other terms also will have a sign according to this limit, and then you can decide whether the system is bivostable or not. If you have an entire row of zeros appearing, then the system is not bivostable. And then you can compute and complete the table with some auxiliary polynomial in order to determining the roots on the imaginary axis. But actually I will not go into this one. If you are interested, you can look at the slides yourself or at the references and try to understand, but we are happy just with this case over here. So let's see an example. So this one is the example for the first special cases. If you are brave, you can try and do it yourself and then check the solution. Otherwise, just wait. The solution is coming up in 3, 2, 1. So let's start again. This same idea. Start s to the power 4, all the s down to power 0. Coefficients: first row 1, 2, 1. Second row 3, 6. Then we start writing down the third line. So third line, 6 times 1 minus 3 times 2, 0. Okay. And for this other line over here, we have basically 3 times 1 minus 0 divided by 3, which yields 1. So we have a problem over here. We cannot continue because we would have a division by 0 basically. So we replace this by epsilon and we continue. So this term over here will be, well, 6 times epsilon minus 3 divided by epsilon. This one turns out to be 0. And then at the end, the last term is basically this thing over here times 1 divided by these things over here, so it gives 1. So now how we see if this is stable or not, if these are all the same sign? Well, these are positive, so we make epsilon tend to 0 on the positive side. So we can say epsilon tending to 0 plus, which is the sign of this guy over here. Well, if epsilon tends to 0, then you have a 0 appearing here, so you have minus 3 divided by something which is positive. Minus 3 divided by something positive is something negative, so this term goes to a negative value, which means that we have a change of sign and this is stable. It is not bivostable, to be more precise. Let's see another example over here. This is an example of the second special case. You can look it up if you wish, but otherwise just be happy to do this part over here. So you can do it, and at some point you have a line all of 0. The system is not bivostable. If you are interested in knowing how many roots you have in the imaginary axis, you can continue with this trick over here. Otherwise, we are just happy to know that this is not bivostable. So let's have some words, final words on the root Hurwitz. It is a simple, let's say, algebraic condition for the stability that you can work out. But there are some nice facts that you can look into. Actually, it is a necessary condition for the stability that all the coefficients of the denominator have the same sign. And yeah, this is kind of it is not sufficient, but it's necessary. So if you see a change of sign in the denominator, well, that's no good already. It's no good already. And there are some special cases of the root Hurwitz criterion, for example, for second order or order 3, that actually turn out to be very simple conditions. So for example, let's focus on this one. As I already introduced to you, if you have a second order denominator have strictly negative real roots if the coefficients have the same sign. If you have a1 equal to 0, then you have purely imaginary roots. But if you have all positive or all negative coefficients, then you are okay. Then the system is this part has a real negative real parts. The roots are real negative parts, and if you have only terms like this as denominator, then they are stable. They are Bibot stable as a necessary and sufficient condition. So most important thing, morale also of the story, this root-Hurwitz criterion is difficult because you use it for computing the stability of a denominator of a transfer function when the denominator is not factorized, when the roots of the denominator cannot be computed easily. But if you have a denominator which is already factorized and you can just read out the roots, well, do not use root-Hurwitz, please. Okay, I say this thing every year, and every year there is someone who does it. So please pay attention. If you already can read the roots, I say it again, if you can already read the poles out of the denominator, do not use root-Hurwitz. You just look at the real part of the roots. Okay, let's look at the final example of this root-Hurwitz criterion, and this is actually one of the examples which I recalled before, in which the use of the criterion is kind of meaningful because it can allow you to discuss a solution, discuss the stability with respect to the value of a parameter. So let's look at this feedback system over here. We want to know whether y over c, the transfer function from c to y, is stable as a function of the gain k, okay, which is basically more or less the same as solving a problem of tuning a controller. We have a scalar control gain. We want to ensure the stability of this transfer function f. We want to know which are the values of k, ensuring Bibot stability from c to y. Okay. So again, you can try and do it yourself. The first thing to do in this case is to compute the transfer function from c to y, this f over here, and then once you have the transfer function, which will depend on k, on this k, then you can apply the root-Hurwitz criterion to figure out for which values of k the system is stable. So solution is coming up here. So first part, computing f. Well, we use the rule of simplifying this scheme. So you remember f will be fraction, numerator direct line from c to y, which is khs, denominator under negative feedback 1 plus khs. If you work out everything and simplify everything, you end up with this one. Now we take the denominator and do the root-Hurwitz criterion. The solution is over here. I will show it in 3, 2, 1. There we go. So root-Hurwitz criterion, starting s to the power 3. There we go. 168 k. Sorry, 68 here for the first row. Second row, 1680 plus k. Now let's compute the third row. 80 plus k times 1 minus minus 16 times 68, which sorry, I got the sign wrong. It's 16 times 68 minus 80 minus k, which gives you this one. Here you get a 0, then you continue here, you get basically this one times this one divided by this one, so 80 plus k. So this is stable when all of these have the same sign, so 1 and 16 are positive, so which means this one needs to be positive. So when this is positive and this is positive, which corresponds to k greater than 80, then minus 80, and k smaller than 1008, we assume k to be greater than 0, so we can say just k before or between 0 and 1008. So let's see actually in practice what it happens. We can just replace k and simulate the system. So if we pick, for example, step response just for h, okay, we take this one away, just put an input into h and look at the inputs in the output response for y, for a step, you could just get this. So h is stable by itself. Let's look at now f. So from c to y, we with f computed for k equal to 1. So we look at the step response. The step is bounded. So if the system is Bebo stable, it means that step response, the output will also be bounded. So as you can see, for k equal to 1, you get a bounded output. Notice that if you have c equal to 1, then y it is not so close to 1. So actually this happens to improve when k increases. So as you remember, for the example we've seen before, with the bigger gain you have the tendency to get y closer to c. So that's actually what it happens. For k equal to 100, we are still stable because it's smaller than 108, and you get this impulse response which is closer to 1. Sorry, this step response. It is still bounded, so we are in the case of a Bebo system again. Let's take 1008. Then in this case we are at the limit, so we have a critically stable system which gives you a step response oscillating forever, never stopping. Also the impulse response would be the same. And if you go beyond this, for example, k bigger than 1008, k equal 2000, then you have a clearly unstable response, oscillatory response going to infinite values, bigger and bigger values, because the system is not Bebo stable, and clearly in this case it is unstable, as we can see by the step response.